Hello everyone, welcome back to the Power Electronics and Laboratory. Today we will discuss so-called the basic electrical circuits. Since power electronics is something dealing with power conversion using power electronic circuit, the knowledge about the electrical circuit is very, very important. Okay, so that's why I'm going to review on key points in electrical circuit, especially about phasor analysis. And also I'm going to review on the concept of power. Okay, I think most of you have learned the concept of power. There are several different kinds of powers, like instantaneous power, complex power, average power, and so on and so forth. So we're going to discuss these definitions on power. And the one key concept of power electronics is switching. Okay, switching. The thing that differentiates power electronics from other courses is we are using power semiconductor switch, switch on and off, on and off. So when switch is operating, the voltage waveform now looks like a square waveform, 구형파, right? When switch is operating, the system becomes no longer sinusoidal. The most of the circuit concept you have learned so far is about sine and cosine. When the voltage source is sine, when current source is sine, you are all familiar with the concept of sinusoidal excitation. But unfortunately, in power electronics, we are dealing with square waveform. Why? Because we are using switching. So what makes this square waveform different from sinusoidal waveform? So have you ever thought about power and circuit analysis based on square waveform? I think you have not. So that's why I'm going to review on the basic electrical circuit concept. Okay? So let me start with a steady state. AC waveforms with sinusoidal voltages and current. Here, an important point is sinusoidal. Okay. Later on, we will discuss pulse or square waveform. So, first, you have to clear your knowledge about sinusoidal. Okay. Let us start with a simple RL circuit with a voltage source connected. And everybody knows that voltage source has cosine functions, cosine omega t. And the amplitude is square root 2 times RMS. This is RMS value, right? RMS. And we are using phasor representation. Phasor. What is phasor? Phasor is a complex quantity. 복소 양이죠. 복소수. Complex quantity. Complex number. Complex number has magnitude and angle. Right? Complex. In complex domain, you have a real axis and imaginary axis. And if you have some number plotted on complex plane, you have an amplitude and this is angle, right? So once we know these two quantities, then we can specify the complex number. So please take a look at this. This is instantaneous value, right? And this is complex quantity. So what we are going from instantaneous, 순시적인, instantaneous value to complex quantity, we have a certain rules. in mathematics, this is called kind of mapping. Okay, mapping. So the amplitude is defined to be same as RMS. Okay, not the peak, but the RMS. And angle is, this angle is defined to be same as the phase angle of the cosine function, which is 0. So this is like a definition of complex quantity, so-called phasor. This is our promise. 하나의 정의죠, 정의. mapping입니다, mapping. Okay, and then, so if we apply the same rules, then the complex quantity of the current is now I, and then the phase angle is minus phi. Please don't be confused. The angle is minus phi. Okay? So we are dealing with this phasor analysis. Why we are using phasor analysis? Why? Because, simply speaking, in linear circuit, linear, you know what linear means. Additivity and proportionality holds for linearity. Okay? In linear system, if the source voltage is sinusoidal, then the current voltage at any place is sinusoidal. 자, 선형 회로에서는 소스 자체가 사인파면 전압이나 전류는 어디에서 어느 포인트를 찍던 어느 메시의 커런트를 구하던 다 사인파입니다. 그게 리니어 회로의 특징이에요. 네? So, which means it's important to know about amplitude and phase. Once you know about amplitude and phase, then you know everything. So, to make the complicated circuit manipulation into simple thing, we only pay attention to amplitude and phase. Okay, that's why we are using phasor analysis. If the system becomes nonlinear, or if the system has some non-sinusoidal excitation, then we have to think about it in different ways. 만약에 회로가 비선형이거나 혹은 입력 전원, 입력 전류가 사인파가 아닌 경우에, 그런 경우가 많습니다. 전력전자에. 그럴 경우에는 우리가 이런 페이저를 적용시키는 거에 대해서는 좀 더 조심을 해야 돼요. That's why I'm gonna review this phasor analysis. Okay? So, like any other courses, you have to know fundamentals very well. Otherwise, you cannot go step forward. You have to know the fundamentals. So this is phasor analysis. Now, once you describe voltage and current using phasor, what about the impedance? Impedance you can also describe as a complex number. Everybody knows that the real term is resistance, and the imaginary terms at this moment is inductive impedance, omega L. So the Ohm's law also holds for sinusoidal case. So the voltage phasor is equal to current times impedance. And so that's why this is called amplitude. This is amplitude of this number. And this phi is phase. Okay? Now, we happen to have same angle, phi and this phi. But everybody knows that the impedance angle is same as the angle difference between the voltage and current. 그죠? 임피던스의 앵글 값은 전압과 전류의 앵글과의 차이죠. 그게 why? Because current is equal to voltage divided by impedance, and the voltage was defined to be V exponential J0, and is jet amplitude exponential J phi. Then everybody knows that the quotient of complex number has the amplitude, which is also the quotient of the amplitude, and the angle is the angle difference, okay, from the denominator and numerator. Okay? 0 minus V. So I hope everybody is familiar with this. Okay, hello everyone. Now we have learned the basic concepts of powers and the power factor and the RMS and some of the phasor analysis concept. Now let's apply those into one example. Okay, this is very famous example, capacitor bank. I think in my experience, this was my graduate school examination. One question was from that examination. So we start with this AC sinusoidal voltage source and resistor and inductor. Okay. So you can think about this as a factory, R and L. Okay. And usually the factory has equipped with a lot of motor loads. The factory has a lot of motors, and motors, as you know, is an inductive load, RL. So the power factor is very low, approaching sometimes 0.5 lagging. So the utility company now asks factory people to upgrade or increase the power factor. 공장 같은 경우에는 역률이 낮기 때문에 이제 그 계통에서 보면 즉 전력 우리로 얘기하면 한전이죠. 역률을 증가라고 합니다. 네? 그렇게 왜냐하면 자기들한테 중요하니까. Under that circumstances, the usual method is to put capacitor bank. Okay, this is the way to improve the power factor. Okay, so this is called capacitor bank. The bank literally means it's not the financial bank. It means like the stack of capacitor. It's a huge stacks of capacitor. 캐패시터들이 이렇게 막 적층된 여러 가지 그러니까 단체로 있는 거죠. bank, capacitor bank. Okay, this is usually size as large as this whiteboard. Okay, or the several whiteboards. Okay. So the question says the V is square root 2 120 cosine 2 pi 60 t volt. So 60 hertz, okay? 60 hertz. So the angular frequency becomes 2 pi 60. And 120 volt is RMS, and we multiply by square root 2. And the load is 1 kilowatt. What is the class of this power? This is average of instantaneous active power, or in other words, real active power. Okay? And then power factor at this moment is 0.8 lagging. What does it mean by lagging? Lagging is lagging behind. So which is leading? The voltage is leading. Current is lagging. Okay? So the lagging leading is defined from the current point of view. 그러니까 전류의 입장에서 얘기하는 거죠. lagging. Current is lagging behind the voltage. So inductive load, the power factor is lagging. In opposite manner, the capacitive load, the power factor is leading, which means the current is leading the voltage. In this case, current is lagging behind of the voltage. So power factor is pretty low, right? 0.8. So we like to have as close to unity as possible. So the target is 0.95. Okay, we like to make it 0.95 by installing capacitor bank. That's our the goal. So the question is now, how much is C is required to make the power factor 0.95? Okay, that's the question. This is a famous question from circuit analysis. Have you ever solved this question before? No? It's first time? Okay, maybe it's... So, now let's start with apparent power. Apparent power, we are using the meaning of power factor. So, power factor was defined to be the ratio between average real power divided by apparent power. So we know power factor, we know we know the load power. So by using this, we can calculate apparent power. So 1 kilowatt divided by 0.8 is 1,250 volt amperes. Okay? Now we are in a good position to calculate Q load. What is Q load? Average instantaneous reactive power. Okay? We take the average of instantaneous reactive power, imaginary part. And that is called Q load. And this is same as Q load is equal to square root of the terms, which is complex power, apparent power squared minus P load squared. Where did it come from? This is coming from this relationship. S is equal to P load plus J Q load. Okay? And S is P load squared plus Q load squared square root. Okay? So from this, we can get this relationship. And if we plug in the numbers, then we get 750 volt ampere reactive var. Okay. And now apparent power, let's compute the new, is P load power factor target (1 kilowatt) divided by 0.95. So this is our target, right? But the P load doesn't change. Why? 왜 액티브 파워는 안 바뀌죠? Of course, because we only add capacitor bank, so the power dissipated only depends on the resistor. So since the resistor doesn't change, the active power is also not changing. Okay? So this remains to be same. 그죠? 액티브 파워는 안 바뀌죠. 왜? 정확값이 안 바뀌니까. 오로지 캐패시터만 더 는 거니까. 캐패시티가 능으로 해가지고 파워 팩터만 바뀐 거죠. 오케이? So, then this becomes 1052.6 volt ampere. Okay? Now we follow the exactly same step as before. Now let's compute Q load new. Okay, so Q load new is now equivalent to 328.7 bars. Okay? So please don't forget that before and after we installing this capacitor bank, the active power P load doesn't change. What it changes is only the Q and then accordingly the complex power S. 그죠? Q하고 S만 바뀌는 거죠. Okay? So this is also same as so new reactive power is now sum of the old Q load minus QC. Where is this coming from? Because of this capacitor bank. Right? The power is conserved. Also the reactive power is conserved. It's like we are adding more reactive power here. And this now QC becomes 421.3 bar. Why? Because QC is equivalent to Q load minus Q load new. So Q load was how much? 750 bar. 750 bar minus 320.7 means QC. Okay? What does it mean? So it's like by adding capacitor bank, we reduce this 750 bar. 그러니까 캐패시터를 닮으로 해가지고 Q reactive power 750바를 줄이는 거죠. 328.7로 얼마만큼? 421.3을 빼주는 거죠. 캐패시터를 닮으로 해가지고. 오케이? So now we are in a good position to calculate the required capacitor or capacitance. QC is equivalent to V squared divided by XC. Okay? I think everybody knows about this. V squared divided by impedance is same as the reactive power. Okay? And this one is now V squared divided by omega C. Okay? V squared times omega C. So, therefore, C is equivalent to QC divided by V squared omega. Okay. So the answer is 77.6 microfarad. So in summary, by adding capacitor bank of 77.6 microfarad, then we are able to improve the power factor from 0.8 to 0.95. Okay? I think some of you are now confused with, but I think this is, can you understand this? This is because of conservation of power. This is like you are adding power, reactive power or active power. So, S nu is equal to P load plus JQ load. Okay. And then minus JQC. Before you are adding capacitor bank, we had this much, okay? And after you are adding this, actually subtracting, you are subtracting this JQC. So power is conserved. Same for active power and reactive power. 이거 약간 개념이 어려울 텐데, 그러니까 파워가 보존된다고 보시면 돼요. 유효 전력도 아니면 무효 전력도. 그러니까 요만큼만 JQC가 빼진다라고 생각하시면 되는 거죠. That's how we improve power factor, right? 그러니까 power factor improve 한다는 얘기는 뭐죠? 결국은 reactive, imaginary part를 줄인다는 얘기예요. 그죠? 어떤 거 imaginary part? S에, complex power에. 그게 정의였지 않습니까? 그죠? 파워 팩터라는 건 정의는 average power divided by apparent power니까 뭡니까? imaginary part가 0이 되면 파워 팩터가 1이 되잖아요. 그러니까 이만큼 빼줘야 되는 거죠. 이렇게. 그럼 요 값은 어떻게 정해지느냐? QC is defined to be generated from capacitor bank and is same as this. 그렇죠? 우리 active power는 어떻게 define 되죠? active power is 전압 제곱 나누기 저항값이죠. 그거 비슷한 겁니다. reactive power는 이렇게. 그리고 캐패시터의 뭡니까? capacitive reactance는 1 over omega c죠. 네. Okay? So far we solved one example. It's about don't forget we are dealing with now single phase sinusoidal case. Now we are going to discuss three-phase system. Three-phase system. Now we have again different kinds of power, same kinds but different expressions. Okay. So in industry practice, these are very famous. This is still popular in industry as a mean to improve power factor. Okay, people still use this kind of technology a lot in factory side. So far we only discussed single phase case. Now we are going to discuss three-phase case. Okay? Three-phase system, I think you have all learned during sophomore or sometimes junior class and in basic electric circuits. And why we are using three-phase is because we like to deal with high power, larger power. So three-phase system is more efficient, more convenient to deal with the high power compared to single phase. That's why we are using three-phase system. Okay. Okay, I think most of you have seen this kind of configuration. This is a typical Y-connected source and Y-connected the load. Okay. In three-phase system, we have two different kinds of connections. One is so-called star, or sometimes called Y connection. Y connection. And what's the other connection method? Delta, right? We have a delta connection. And in some literatures, we use the term star connection, okay? Star connection. And why we are using the shape of Y or delta? It doesn't have to be Y. You don't think so? We can actually have this, right? This is also a star connection. Why we are using this shape of Y? Because it symbolically represents the angle difference. So it's kind of the mixture between the real situation and the mathematical interpretation. 그러니까 실제로 이렇게 Y로 여러분 안 생겨도 돼요. 근데 왜 자꾸 Y로 보여주느냐? 그 앵글 디퍼런스가 120도만큼씩만 차이 있다는 거, 즉 복서 평면상에서 앵글이 이렇게 120도만큼씩 차이 있다는 거를 심볼릭하게 보여주자 보니까 이렇게 Y가 된 거죠. 네. 그렇습니다. Don't be confused. The real connection could be like this. The important point is you connect at the midpoint here. Okay? Same thing for delta case. It's okay, you can make a circle. Huh? It's okay, but the important thing is you connect like a loop. Okay? That's the only difference. So the advantage of three-phase system is, most of all, efficient processing of high power. So I will only list two most important example or advantages. Efficient processing of high power. Actually, this is quite relative term. 상대적인 건데요. As compared to the single phase case. Okay? You can think about three different single phase. Okay? If you compare one three phase together with three sum of single phases, this three-phase system is a lot more efficient. 그러니까 세 개의 서로 다른 싱글 페이스보다 세 개의 싱글 페이스를 합친 것보다 하나의 three-phase 시스템이 더 효율적이다. 그거에 대해서 제가 다음 시간에 설명해 드릴게요. And the second point is that instantaneous power is a constant. Constant means if we plot this time and PT, which is instantaneous power, is a flat. Flat. In single phase case, this instantaneous power has a ripple having the frequency of twice the input frequency. Right? This black one is, my drawing is not so correct, but the drawing is, the black one is about single phase case. Now the three-phase case is like constant value. It has no ripples. So when we apply to the motor load, actually it doesn't have any torque ripples. So it's very smooth and constant. So because of these two most representative advantages, we are using three-phase system. And this is not exception for power electronics. Power electronics, we are dealing with three-phase a lot. Sometimes we are changing from three-phase to single-phase to three-phase in power electronics. Okay? So next lecture now we will discuss more detailed thing about this three-phase circuit. Okay? Thank you. one class of definition called instantaneous is called in 순시전력 in Koreans, and average power, 평균 전력, and also we have complex power, and we have active and reactive power, active and reactive, 유효 and 무효 in Koreans. So it's important to have some systematic coordination between these. Okay. So from now on, you have to think that oh, power has instantaneous values and average values and complex, and it has two different approaches or concept, active and reactive. Okay. And so we studied single phase case. Now if we extend our theory to three phase case, okay. So before we talk about three phase case, now let me show you some brief characteristics of three phase case. This is three phase. What is the three phase? The definition of three phase is we have three different sinusoidal systems having the same amplitude, but the phase is displaced by plus 120 degree and minus 120 degree. So this is VA, VB, and VC. And we have also this three-phase load. And why are we using three-phase case, not four-phase, three-phase? Why not about six-phase? Why not about five-phase? So what's the advantage of three-phase? It's important to know about advantages. Of three-phase system. I think the most popular type that you can find out these days is three-phase. Okay? The power is transmitted in terms of three-phase case, and in factory, in large building, all the electric power supply system is configured using three-phase system. Why? The first advantage is it has the least necessary number of wires. First, single-phase case. Number of wires. In single-phase case, how many wires do we need? In single-phase case, how many wires do we need? Two, right? Single-phase case, we need two. Don't we? Yes, we do, right? 선이 두 개 필요하죠? single-phase case는 플러스, 마이너스. What about the two-phase case? Have you ever known that we have a two-phase? Yes. The angle is different by 90 degrees. Then it is called two-phase systems. So actually it is used in some place. And two-phase case, how many wires do we need? 3 neutral wires, and the one with phase A, one with phase B, right? So we need the 3 wires. And for a three-phase case, how many wires do we need? In this case, it seems that we need 3, because the neutral path, ideally speaking, is not necessary, because everybody knows that on the balanced system, this potential is equal. When potential is equal means, even though we connect by wires, there is no current flowing, right? The current can flow as long as there is a voltage drop. So since we don't have a potential difference, we don't have a current. So when we don't have a current, we don't need the wires. So we only have 3 wires. So it means now the number of wires is very optimized as a 3. So optimized means is cheap, cost effective. So we use three-phase system to dispatch the power for a long distance. So that's the one major advantage of three-phase system. Now, what's the other advantage is, maybe I can say that this is advantage 1. And the second advantage is, so second advantage is, it's like, let me tell you the conclusion first. What is PT? PT is this. And PAV is this. So instantaneous active power is exactly same as average power. It means there is no ripple on instantaneous power. This is extremely important advantage. So if I draw using the graph, if I show you instantaneous power for the single phase case, okay? In single phase case, if you describe instantaneous power, it looks like this. And the oscillatory frequency is 2 omega t. So it means now power is oscillating as twice the input frequency. And this average value is equal to PAV. In single phase case, this is a single phase. What about three phase case? In three-phase case, instantaneous power has no ripples on it. It has same value as average power. Right? This is amazing, right? This is amazing. So once you hook up this induction motor to three-phase case, the power doesn't have oscillation, which means we can transform the power concept into torque, okay? Because power is equal to torque times speed. So when there is no ripple on power, that means there is no ripple on torque. Torque means a force on motor. So it means there is no vibration. So in three-phase induction motor, there is no vibration under the three-phase case. So you can think about the cars. I know that how many pistons do we have these days? 4 pistons? 4기통짜리 차들이 많죠? 그 기통수가 바로 이 페이스하고 마찬가지예요. 그죠, 여러분들? 그 차의 그 4행정 사이클로 차들이 뭡니까? 그 여러분들 공업 시간에 배우셨나요? 뭐 압축, 폭발, 뭐죠? 팽창 배기인가? 그 사이클이 그 피스톤마다 다르게 동작을 하죠. 왜냐하면 팽창할 때 그 힘으로 차가 달리니까 그 팽창하는 걸 한꺼번에 쫙 하게 되면 차가 진동이 생기니까 그거를 서로 위상차를 줘서 차가 여러 번 터지게끔 해가지고 그 힘이 골고루 전달이 되는 거죠. 그래서 기통수가 많을수록 차가 승차감이 좋은 거 아니에요. 그래서 뭐 링컨 캐딜락 같은 경우는 뭐 심하면 뭐 6기통 막 그러잖아요. 네? 이것도 똑같은 개념입니다. 3페이스는 3기통짜리여가지고 그게 서로 파워를 골고루 120도만큼씩 서로 차이를 둬서 결국은 이게 깨끗하게 가는 거예요. Okay? This is, I think, outstanding advantage of three-phase system. This one. So that's why we are learning three-phase system here. So, if I show you in more exact way, here. So the source voltage will have the same amplitude, and it has 120-degree phase shift. In this case, we have a minus here, and in case we have a plus. And actually, we can have a different voltage, a different sign. This could be plus, and this could be minus. Still, in those cases, we can call it balanced, 평형. So it means we have two different types of balance system, positive way or negative way. This is called positive way balanced. Here, what is this? This is a phasor diagram. This is a time domain. We change to the phase domain. What is the phasor? I have explained last lecture that phasor is a complex mapping having the amplitude same as the RMS and the angle is same as the phase. So once we describe this phasor of this three-phase time system, we can have VA and VB and VC. So this is a positive-wise balance system. If we have a negative-wise balance system, means this is VA and this is VC and this is VB. Okay? But the industry standard is this is the positive manner balanced. So if I tell you one little caveat, if we have a unbalanced system, which means now the amplitude is different or the angle is different, then we will have some kind of ripples. This is when unbalanced. Unbalanced. Okay? So when the system is no longer balanced, then we start to have some oscillatory component. This is pretty bad. Okay? But in this semester, we will not consider this oscillatory nature. We only assume that everything is balanced. By the way, this is my favorite topic to discuss. One of my favorite topic. Actually, this three-phase system is developed by the person called Tesla, right? Tesla, and well, I don't know. Actually, he's the first guy who invented three-phase system, but he's the one who invented induction motor and three-phase system. He hooked up the induction motor to the three-phase system. So, and those days, he was competing with Edison, and Edison was fond of DC. So he's a DC guy, and Tesla was AC guy. And Edison was a strong supporter of the DC power transmission. But as you know, that the most important part for the power dispatch is you have to step up the voltage. So in order to step up the voltage, that you need a device called transformer. So in order to use transformer, then AC was the only way to implement this, stepping up the voltage. And then Tesla was, backing up this three-phase system, and also he mentioned that three-phase system there is no ripples. So induction motor is quite smooth and there is no sound. So Tesla was the inventor of this kind of theory. Then, as you know, Edison was quite strong-minded person. Actually, Edison was told to be very, how can I say, strong-minded. Very. His personal character is very strong. He's like some kind of egoistic but anyway, so he really hated three-phase system. So one argument that he has over this AC is that three-phase system, as you know, if you add these three voltages, then the sum would be 0, right? And Edison questioned this. This is ridiculous. This is impossible. Why? How can something become 0 once added? 합쳐서 0이 될 수가 없다는 거죠. He said that's against the nature. If something is added, then it should have some value. It cannot be 0. Of course, in those days, he wasn't people couldn't accept this. So that's why we're using AC. But these days now, if I look back at his comment, I think I completely agree with him on his point, because we need this neutral line, right? So the point that I said we only need 3 wires is wrong. Actually, we need one more line, neutral wires. Why? Because the real system is not balanced. Real system is not balanced. So we have to have some kind of preventive neutral path to carry over this neutral current. And also, there is a slight unbalanced nature in the load, so we have some oscillatory nature. So Edison was quite right that the summing up to 0 is against the nature. So now we are now shifting from AC power transmission to DC these days, high voltage DC power transmission. So it's quite interesting to read this article about the competition between AC and DC. Okay. So now come back to our explanation of a three-phase system. Now, once everything is balanced, so these semesters I always assume balanced system. So this is also the current, and we have some phase angle difference. This is due to the load impedance angle, right? And this phi now appears at this point. Okay, so this is three-phase phasor system. Okay, now let me discuss now this instantaneous power. Now let's start with instantaneous active power first. What is the definition of instantaneous active power? Is PT is equal to VAIA plus VBIB plus VCIC. Okay? This is quite straightforward. And once you look at your class note, then this was for the single phase case. PT. Okay? But since we have a three-phase system, we just added 2 more terms. Phase B and phase C. Now what about the instantaneous reactive power? Now we use the term Q, and this was defined to be VA prime IA plus VB prime IB plus VC prime IC. And what does prime means? The 90-degree phase delayed of VA. So which means okay. So originally we started with the cosine omega t for the VA, right? So if something is delayed by 90 degrees, then we just subtract minus 90 degrees. That's the definition of prime. I think most of students didn't see this before. This is the first time, right? So this is actually the original definition of instantaneous reactive power. Of course, for the single phase case, this is Q2. QT for the single phase case. Here I just added two additional terms to match the three-phase case. So some of students might ask question, why 90 degree? Why 90 degrees? So, in complex domain, this is the imaginary axis, right? Imaginary variable. So imaginary is kind of 90-degree phase shifting. So, but, to tell you the truth, the first one, the instantaneous active power, is accepted by many people. This is almost like a standard. But in opposite, this QT, the definition of QT is still now under discussion. A lot of engineers, scientists are working to define reactive power in more rigorous way. Okay, so it's quite interesting to see that the definition of reactive power is still going on, right? Still going on. Maybe you can come up with a new definition of reactive power. Why do you think so? Why do you think the reactive power definition is still not defined or still going under discussion? Because active power is something that you can measure, something you can feel, but the reactive is like imaginary things. So due to this imaginary characteristic, people can come up with many different kinds of definitions. 즉, 이 reactive power는 여러분 일종의 보면 좀 이 형상화된 정의입니다. 예? 그래서 실제 active power 같은 경우에는 여러분 이거는 이제 많이 접해보시고 실제 이런 것들이 많이 쓰이는데 reactive power 같은 경우에는 단어에서 의미하는 대로 좀 imaginary죠. 상상 속에. 그러니까 여러 다른 형태의 정의들이 가능해요. 특히나 언밸런스일 때 또 사인파가 아닌 경우에 하모닉이 있는 경우에는 더 복잡해집니다. 이 리액티브 파워 정의에 대해서. 그래서 여러분들도 혹시 이쪽 분야에 관심 있으면 나중에라도 연구하셔서 아마 여러분들의 이름을 따서 무슨 리액티브 파워라고 하셔도 돼요. 실제로 그런 학자들이 많이 있습니다. 네. Okay? So that's the definition of instantaneous reactive power for both active and reactive. Now, what about the average case? Average is pretty simple. You just average. So, average instantaneous active power is you just integrate an average This is PAV. And under this particular case, what we have obtained is 3VI cosine phi. And here you notice that this is same as the real power of complex. Real part of the complex. So, complex power is same as average power. Okay? As a conclusion, complex power is same as average power. In some sense. So, the real part of the complex power is 3VI cosine phi. Okay? Now, let's compute the average instantaneous reactive power. So we use the symbol QAV. And also this we can define in the same manner, QT, dt. And once you apply this calculation, that you obtain 3VI sine phi, which is same as imaginary part. I think as electrical engineers, you need to do this by hand at least once. Don't just memorize this. You have to compute this, okay, and find out this. 그러니까 여러분 적어도 전기공학과 졸업하시고 그다음에 전력전자 들으신 분들은 대부분 4학년 학생들일 텐데 이건 다 아실 거예요. 근데 직접 한번 손으로 계산해 보세요. 어떻게? 요 식을 쓰셔가지고 PT를 구해보세요. 그러면 어떻게 되죠? 코사인 곱한 게 총 6개 이제 항이 나오고, 3개 나오죠? 요거를 한번 적분을 해보세요. 그 적분 공식을. 그러면, 사인의 곱은 여러분 그거죠? 제곱으로 되면 합차로 바꾸는 공식 있죠? 그걸 통해가지고 하면 요 3B의 코사인 P가 나옵니다. 이것도 마찬가지. 그거 한 번은 여러분 해보시고 졸업하셔야죠. 그냥 외우지 마시고. Okay? So once you have done this by your handwriting, that you have a complete understanding. Now, this complex power is equal to PAV plus JQAV, right? So you can define or you can understand the complex matches or corresponding to average power. Okay. Now, going back to our advantage of three-phase system, this 3VI cosine phi is exactly same as this. Right? I told you once that instantaneous power is equal to PAV. Okay? This is interesting, right? This value itself is equal to PAV. And if you integrate this and divide by t, then also it has same value. 그 재밌죠, 여러분? 이렇게 실제로 했을 때도 PAV가 나오고 이거를 평균 취했을 때도 PAV가 나온다는 얘기예요. 네, 이것도 한번 여러분들 직접 손으로 계산하시기 바랍니다. 이건 삼상 시스템의 중요한 장점 중에 하나이기 때문에요. Okay? Now we have one more power to define, which is apparent power. I'm now running out of space. Here, let me see, apparent power. 피상전력, apparent power. And this was defined to be 3 VI. Okay? In single phase case it was VI, but now it's three phase. And this is same as the amplitude of complex power. Okay? Amplitude. When you obtain amplitude in complex variable, this is like this is the amplitude, right? You square the real part and square the imaginary component, and you summed and then square root. And this would be equal to 3 VI. Because cosine phi, sine phi, once you square and plus, then it becomes unity. So you have only 3 VI. So this apparent power means like 피상전력, apparent power. Apparent means 피상, right? Among these all various power, what we are paying to the utility company is this average power, right? An electric bill that you are paying every month is this one. Okay? 적산전력계로 여러분 돈 내는 건 이거죠. But what the utility company is investing on the power line, or what utility company is building the system is based on this. Utility company, 한국전력, they set up transformer, power line, circuit breaker, all these measurement tools based on this. Why? Because the system should withstand the voltage and current at the same time. So I'm going to introduce later the factor between this apparent power and average instantaneous active power, which is called the power factor, right? Okay, so today we have discussed this power concept in three-phase system. So based on this power concept, we will analyze and design the power electronics converter, AC-DC, DC-DC, DC-AC, and AC-AC converters based on these parameters or powers. So please review and keep these in your mind so that you are able to analyze the power converter circuit easily. Okay? Thank you very much for your attention. Bye.